welcome back. We're on part 2 now of our lecture for the second day of chapter 2, and we're going to be talking more about now precipitation in the atmosphere and how precipitation on Earth might be changing, or why it might be changing, and is there any evidence it might be changing as a consequence of global change. And so, of course, the first question we need to be asking ourselves is, why would we think that there might be changes in the global amount of precipitation associated with global warming? And as I kind of alluded to at the beginning of this lecture, it's not the greenhouse gases itself. It's not like carbon dioxide changes how the processes of precipitation work. You know, back in like ATSEVS533, when you learned about like condensation and collision and coalescence and the Evaporation process, carbon dioxide has nothing to do with that. Methane has nothing to do with that. It's not the gases themselves, it's how the gases change the surface temperature, and in particular how they change the evaporation rate. I mean, we're going to be changing how fast we put water vapor into the Earth's atmosphere. Now, evaporation off the surface of the ocean is in fact affected by lots of different factors. Probably not all that surprisingly, it's affected by wind speed. The faster the winds are blowing, the faster evaporation is happening. It's probably a little bit more surprising that the roughness of the surface of the ocean matters a great deal in terms of determining the amount of evaporation. Now, roughness and wind speed are often related, but the rougher the ocean is, the more effective it is at transferring water from the liquid state in the ocean to the atmosphere. The humidity of the overlying atmosphere matters too. I mean, there's only so much water vapor the air can hold at any given time, and so if the air already is saturated, you don't get a lot of evaporation. And temperature. Temperature of the air, temperature of the ocean, they both matter. Now, in practice, the temperature of the air and the temperature of the ocean tend to be very close to each other. Let's focus, though, on this idea of temperature, because temperature is the one that we most certainly have a connection to greenhouse gases with, okay? I am not so ready to think about changes in wind speed and temperature and greenhouse gases. I'm not so ready to think about changes in the roughness of the ocean and greenhouse gases, and I'm certainly not yet ready, well, I will be by the end of this lecture, to talk about changes in humidity and greenhouse gases, but temperature we got under control. So let's focus on that one. Sorry, I'm having some trouble with my tablet today. I think I got too many apps open. Okay, so we are going to work on that fourth one, how temperature affects the rate of evaporation off the Earth's oceans. And this pulls up an old friend. Now, this might not be your friend, but you actually learned a great deal about this back in ATSEVS533. Depending on whether you took it with me or with one of the other instructors, you know that there is a relationship in the atmosphere called the Clausius-Clapeyron equation. Now, in intro, we generally don't show you the equation because it just scares people. I mean, showing the equation is not so hugely important in the context of intro. But this is a 500 level class. We can swallow this. You know, this is not the worst equation you're ever going to see in your life. It's called the Clausius-Clapeyron equation. Again, in ATSEVS533, you may or may not have heard that term. But it is a relationship between the temperature and the amount of water vapor in the Earth's atmosphere. Now, it looks horrible, but actually most of the terms in it are just constants that you would be plugging in your calculator. Now, I'm not going to make you do problems with this in this class, you know, like as in plugging in numbers. I have every confidence you can use your calculator. That's not the point. So E naught, script L, RV, T naught, they're all interesting concepts that come to us from physics. We don't care about them right now. It only leaves two other variables in this whole equation here. There's ES and there's T, and unsurprisingly, T is the current air temperature. Okay, and ES. ES is the saturation vapor pressure. Now that's a term you do actually learn in the intro class. Saturation vapor pressure is a measure of the amount of water vapor the air can hold under the current conditions. Doesn't mean the air is holding that much. It's saying this is how much water vapor the air is capable of holding under the current conditions. And as you can see here, well, to whatever extent you're willing to approximate it with that squiggly equal sign, it only depends on air temperature. Okay, there's a tiny dependence on pressure. There's a tiny dependence on a few other things. But to a good approximation, this works just fine. And Clausius-Clapeyron, the Clausius-Clapeyron equation then tells us that the amount of water vapor the air could be holding, not necessarily how much it is, but how much it could be holding, is over there on the left-hand side, and all it depends on, in a messy sort of way, is temperature. Okay? You learned that in intro. you learned in intro that we can say that warm air holds more water vapor, or can hold anyway, more water vapor than cold air can. This is actually the mathematical expression for it. And, okay, well now, notice I'm saying here, by the way, that the current air temperature tends to be the same as the current temperature of the oceans themselves. When the air at the surface is touching the ocean for long periods of time, the ocean's a lovely heat sink. It just keeps the temperature of the air and the temperature of the ocean about the same. So, well, if we're going to have higher sea surface temperatures, which we have reason to think is going to happen, that means that the air near the surface over the ocean should be warmer too. And by Clausius-Clapeyron equation, we should be able to guess that there should be more, well, there should be at least the ability to hold more water vapor in the Earth's atmosphere. Now that equation is kind of a mess, kind of an ugly thing to look at. And it's not the kind of equation that you can very easily just look at and go, oh, I see, as temperature goes up, the ES is going to, the saturation vapor pressure is going to go up. It works better to make a graph, like this little graph from an Excel spreadsheet, where they have temperature on the x-axis and that ES, that saturation vapor pressure, on the y-axis. And again, the units are not so hugely important, and I mean the temperatures in Kelvin, but whatever. But you can see that temperature and the saturation vapor pressure are very strongly related. I mean, you could pick any given temperature along the x-axis there, and you could then read across and to the graph and then read over to the y-axis, and that will determine the amount of water vapor that the air would be able to hold if it were saturated. Remember that word saturated from intro? Saturated means like the air is now holding as much water vapor as it is capable of holding. And you can see from this graph here clearly as temperature increases, the saturation vapor pressure increases too. I mean, that's just the nature of the Clausius-Clapeyron equation that we used even in ATS-113. We didn't look at the equation, but we understood what it meant. In fact, that graph in the background there is reproduced in a prettier way in the intro textbook. So in ATS-113, this always came with the caveat that this was the amount of water vapor the air could hold. Because in ATS-113, we often warn that that doesn't necessarily mean that this is the amount of water vapor in the air, since the air may or may not be saturated. Well, that's lovely for like little story problems in ATS-113, but in the real world, where 70% of the Earth's surface is ocean, and the air is sitting there on, at the surface, basically in contact with the ocean, there's been plenty of time for evaporation to happen. Air near the surface over the ocean probably is saturated. Okay? Or very, very close to saturated anyway. So, that graph of the Clausius-Clapeyron, yes, strictly speaking, it's telling us how much water vapor the air could be holding over the ocean, but in practice, that's probably telling us how much water vapor the air really is holding. So, because the air is probably saturated. If it isn't, obviously, that would be a different story, but for most cases, we can kind of start thinking of the air as being, how much water vapor the air is holding as being very directly related to how warm the air and the ocean are. Now, that means that as the oceans get warmer and the air at the surface is getting warmer and so on, well, the air can hold more water vapor. So there's probably more evaporation of water off of the surface of the ocean to fill up that need, right? We now have a greater amount of water vapor the air can be holding. So we're going to need more evaporation to fill that air, that water vapor, to reach saturation, right? So a warmer world apparently has more evaporation. Now you might think that that process would sort of level off, like, okay, now we've hit the new amount of water vapor the air can hold, and therefore we can slow down our evaporation rate again. In fact, it kind of makes it seem like once the atmosphere would be saturated over the surface, there wouldn't be any evaporation anymore. But that's missing the point that there is also a process, though the evaporation of water off the surface is a source of water for the atmosphere, a source of water vapor, but we have a continuous sink of water vapor too, where water vapor is being converted back into liquid water droplets, cloud droplets, and being dropped back at the ground in the form of precipitation. We have to keep replacing that water vapor that is being converted into liquid water and turning back into rain. It's a continuous process of evaporating more water vapor to replace the water vapor that's being precipitated out. And that process is pretty fast. the residence time of water vapor in the Earth's atmosphere is pretty short. If that word residence time isn't something that you happen to remember from like ATS-113, where we kind of make a big deal about residence time, the residence time for water vapor, the residence time of a gas in general, is the average length of time in which a substance, like a gas molecule or whatever, is in a given location or condition. So like, how long is that water molecule in the form of water vapor in the atmosphere before it converts back into liquid water in the form of a raindrop? And in the case of the atmosphere and water vapor, it's pretty short. It's like 10 days. Water vapor is very quickly being converted back into liquid water that falls back to the surface of the Earth. That's in contrast to other gases in the Earth's atmosphere like carbon dioxide, which have a residence time on the order of like hundreds to thousands of years, where a given carbon dioxide molecule, once we put it in the atmosphere, is going to take a long time to leave. Well, in the case of water vapor then, we have a continuous process of getting rid of the water vapor, changing it into liquid water droplets, dropping it, so we're going to continuously have to be evaporating. So we are continuously evaporating water off the surface of the ocean to replace the water vapor that we have condensed out. This drives a faster and faster hydrologic cycle. We should have more evaporation, so we should have more precipitation. I mean, in the long run, the rate of evaporation and the rate of precipitation should be the same, at least globally. But does that mean every place on Earth? Does that mean we're going to have to figure out what that exactly means. But before we do that, let's answer a couple quick questions about what I just told you. Question 3. What is it that we actually learn again from the Clausius-Clapeyron equation? A, how much precipitation must fall to maintain the current temperature. B, how much precipitation should fall at the current temperature. C, how much water vapor the air is holding at the current temperature. Or D, how much water vapor the air could be holding at the current temperature. Which of those is what we get from the Clausius-Clapeyron equation? Make a choice from those 4 options and get a little feedback before we move on to question 4.